Okay, this method is going to be part of chapter 3, but I listed it as optional because sometimes I teach it and sometimes I don't. But when I first learned it, I was told that by the professor that we're going to take a right on the tangent line. And what this method will do is it'll help you approximate real zeros of a function. So let's take a look at how it works. Let's say that you have a function that's continuous on some interval, a closed interval a to b, and then differentiable on the same interval on the open interval. So if you evaluate the function at the left endpoint of the interval and evaluate the function at the right endpoint of the interval, and you get different signs, then we know the function must cross the x-axis. So that means there is at least one zero in that interval. So that's from the intermediate value theorem. So what we'll do is we'll pick some number in the interval as our first estimate of the root. So we'll call that x1. And we will assume that the tangent line of the function at x equal x1 will also cross the x-axis near x1. So in other words, the derivative of x1 will be the slope of the tangent line at the point where x is x1. And we can use the point slope form of a line to find its equation. So if we're considering the tangent line at the point x1 and its corresponding y value f of x1, then using the point slope form we would get y minus y1, which is just y minus f of x1, equals the slope at x1, which would be the derivative at x1, and then times x minus x1. And then we can solve this for y and get that y equals f of x plus f prime of x1 times x minus x1. Now, we're going to let y equal 0 to find where this tangent line crosses the x-axis. So we'll set this equal to 0. Basically, we're looking for the x-intercept of this tangent line. And through a little bit of algebra, we can isolate the second term by moving f of x1 over. And then we can divide both sides by this f prime, and then that leaves us with x minus x1 equals minus f of x1 over f prime of x1, and then find that x equals x1 minus f of x over f prime of x, or actually f of x1 minus f prime of x1. And we can call our new value x2. So basically we could say x2 is x1 minus f of x1 over f prime of x1. And then we could continue this process and say the third point would be x2 from above minus f of x2 over f prime of x2. So the formula for the point xn would be xn is x of n minus 1 over f of x, x of n minus 1 minus f of x of n minus 1 over f prime of x n minus 1. And this is called Newton's method. And you'll better understand this if I can show you an example. Okay, so I'm going to take this function, and let's suppose I want to find a 0. Now I realize this is a function you can actually easily solve algebraically, but let's use it with the Newton's method. Let's say I want a positive root. So I'm looking for a positive root. Well, if you plug 2 in, you know that f of 2 is negative 3. And if you plug 3 in, f of 3 is positive 2. So you know that f of 2 is negative and f of 3 is positive. So by the intermediate value theorem, there must be a root in this interval. So we're going to start with, just choose the point halfway between 2 and 3, 2.5. Now I'm only going to go through 2 iterations, but before we get started, You can easily solve for the positive root, by the way, and see that it's square root of 7, which is 2.64575. But now on other examples, you can't solve it this way, so you're going to have to use Newton's method on other examples. All right, so what we need is we need the derivative. To apply Newton's method, we need the derivative of f, which is 2x. Okay, so now let's get started with Newton's method. Now, you'll need a calculator to do these calculations. So grab your calculator, and remember x1 is 2.5. So Newton's method says x2 would be that same number, 2.5, minus the function at 2.5. So you'd have to plug 2.5 back into the function, and then divided by the derivative evaluated at 2.5. So you'd plug 2.5 back in the derivative. So evaluate the function at 2.5, the derivative at 2.5, and then find their quotient. And then once you get that quotient, subtract it from 2.5. Well, when I subtracted this from 2.5, I actually got 2.65. So now that's x2. So now to get x3, I do the same thing, but instead of doing it with 2.5, I do it with the new value, 2.65. So now I do 2.65 minus the function evaluated at 2.65 divided by the derivative evaluated at 2.65, and then just subtract that from 2.65, and I get 2.6457. Now I'm going to use this to get x4. So x4, I would do this again with the new value, 2.6457. And so I subtract from that the function evaluated at 2.6457 divided by the derivative evaluated at 2.6457. And when I complete that calculation, I get 2.64575. And notice, to 5 decimal places, after 3 iterations, I've got the exact answer, or not the exact answer, but the approximation out to 5 decimal places. So graphically, it looks like this. The blue line is actually the actual function, and the red line, that's actually going to be the tangent line. So remember, what I did is I found I tried 2.5 first, and then what I did is I actually found where this tangent line, see 2.5, the tangent line at 2.5 would be right here. And then by setting the tangent line equal to 0, I was able to find where the tangent line crossed the and that was at 2.65. Well, then I did it again. So at 2.65, that was actually up here on the function. And then when I found, you can't hardly see the tangent line because the lines are so close to one another, but the tangent line crosses the x-axis at 2.6457. And since the third representation is so close, I won't do that. But you can see where that tangent line crosses the x-axis is pretty much the same place where the original graph crossed the x-axis. Okay, let's do it one more time for this function x cubed minus 5x plus 2 on the interval 0 to 1. First of all, if you evaluate the function at 0, you get 2. If you evaluate the function at 1, you get negative 2. So by the intermediate value theorem, there must be a root, at least one root between 0 and 1. The derivative is actually 3x squared minus 5. So I'm going to start with halfway between 0 and 1, which is 0.5. So I'm going to start with 0.5, and then I take 0.5 minus the function evaluated at 0.5 divided by the derivative evaluated at 0.5, and you can see my calculations here, and I got 0.418. Well, now I do the same thing with 0.418. I take 0.4118 minus the function evaluated at 0.4118 divided by the derivative evaluated at 0.4118, and I got 0.4142. And then I do it again at 0.4142 and take 0.4142 minus the function evaluated at that number over the derivative evaluated at that number, and I got 0.4142. So I'm going to estimate that the answer is 0.4142. And if you want to see just how close we got to the 0, plug 0.4142 into the function, and you can see that what we would get is a very, very, very small number. So obviously we do have the 0 to this function that's very accurate. But if you need more accuracy, then you can just take this out to more steps. Now, the method is not always perfect. It could fail. Let me show you an example where it fails. So we know that the solution of this equation, if you set that equal to 0, 0 is the solution. So let's try to find it from negative 0.2 to 0.2. Well, if you were to try a number, say, let's say you tried 0.1 in there, okay? Well, 0.1, if you do 0.1, you get f of 0.1, and you get 0.1 minus f of 0.1 divided by f prime of 0.1, which gives you negative 0.2. But when you plug negative 0.2 in and subtract f of negative 0.2 over f prime of negative 0.2, you get 0.4. So it gets farther away from the actual answer. And then if you do it again with 0.4, you actually get farther away from the actual answer. So I wonder what's happening here. Why aren't we getting closer to the answer? Well, here's what's happening. Now you know right here the answer is 0 because that's where the graph crosses. But if we try 0.1 here, then we actually get this value on the graph. But look what happens to the tangent line. The tangent line crosses way over here. And then if we use that value, then look what happens. We're at negative 0.2, and our tangent line crosses, hits the graph right here, but the tangent line crosses the x-axis way over here. So in essence, we actually are getting farther and farther away from the actual solution. So that's an example of where the process fails. So generally, one of the reasons the process fails is because of the steepness of this graph here. We're so close to the point here, and since this graph is real steep here, the tangent line throws us way off of our path, and that can cause problems, as you can see. So for polynomials, this generally works very well, but for other functions, it could cause you some issues. So that's pretty much Newton's method in a nutshell, and I've got one more optional method or optional topic that I want to talk about for Chapter 3.